This entry-level desktop diode laser operates at 450 nanometers in the visible blue spectrum. It processes wood and leather with high efficiency, but against a sheet of clear acrylic, the exact same laser does absolutely nothing. The photons transmit right through the medium, leaving the plastic intact. There is a common assumption that a laser is a universal heat beam, a tool where higher wattage automatically translates to a deeper cut. In practice, raw power is irrelevant if the beam cannot couple with the substrate. This is the principle of optical absorption. A laser only affects a material if its atomic structure absorbs that specific wavelength. If it doesn't match, the energy is wasted, either reflecting off or transmitting straight through, regardless of the machine's power. In modern manufacturing, the specific atomic vibration of the material dictates the precise wavelength required to process it. Organic materials, wood, leather, and most polymers, exhibit peak absorption at the 10.6 micrometer wavelength. This is the mid-infrared range produced by carbon dioxide lasers. We can deliver this energy two ways. On the left, a continuous DC glass tube drags thermal energy, leaving blurred, scorched edges. On the right, an RF metal tube drops rapid digital pulses, achieving photorealistic detail without thermal drag. Shifting the wavelength slightly can produce an entirely different physical reaction. While a standard 10.6 micrometer beam melts PET plastics, tuning the laser to 9.3 micrometers causes a microscopic foaming reaction. This produces a crisp white frost mark without compromising the container structure. Combining precise infrared wavelength selection with digital pulse modulation allows for high-speed industrial marking without the risk of thermal degradation. Metals present the opposite challenge. They reflect the mid-infrared radiation of CO2 lasers, but absorb the near-infrared wavelengths generated by solid-state and fiber systems. The MOPA fiber architecture offers a level of control that standard metal markers cannot match. By separating the seed poles from the amplifier, MOPA systems allow the operator to adjust the duration of each pulse independently from the total power output. This temporal control enables the creation of permanent, vivid colors on bare stainless steel and titanium, entirely without the use of pigments or coatings. Through thin film interference, precise pulses grow a transparent oxide layer. When light hits it, one wave reflects off the top, another off the substrate underneath. As they recombine, they interfere. Controlling the layer's exact thickness determines which colors amplify or cancel out. For highly reflective copper, which rejects infrared light, engineers utilize wavelength beam combining. This merges the output of multiple blue diode emitters into a single, high-intensity beam. Because bare copper absorbs blue light exponentially better than infrared, this allows for stable, high-power welding and cutting. Controlling the temporal shape of a pulse, or merging specific wavelengths, has transitioned metal processing from raw ablation into precise thermodynamic metallurgy. High-precision manufacturing often encounters a limit where even minimal heat becomes destructive, specifically in medical implants or microchip fabrication. Excimer lasers operate in the deep ultraviolet spectrum, using high-energy photons to break chemical bonds directly. This allows for cold ablation, where the material vaporizes without conducting heat into the surrounding lattice. These systems project immense pulse energies through optical masks. This projection method allows semiconductor manufacturers to etch millions of microscopic features across a wafer simultaneously. To eliminate thermal damage, we deliver energy faster than the material conducts it. Standard lasers heat the lattice over picoseconds, but femtosecond lasers pulse in a millionth of a billionth of a second. Electrons instantly eject as plasma before transferring heat. Outrunning the physics of thermal transfer has enabled athermal machining, a requirement for the most delicate components in the biomedical and aerospace sectors. From the microscopic level, the commercial laser market appears as a complex, highly specialized ecosystem. Industrial capabilities are now defined by a rigid matrix of technological silos, where the success of a project depends entirely on the correct pairing of wavelength and pulse duration. Modern photonics relies on the precise quantum-level manipulation of matter, leaving the era of simple high-heat cutting behind. For engineers and buyers, navigating this absorption matrix is the difference between a failed prototype and a flawless product. To see deeper technical breakdowns of these systems, subscribe to Reticle Red.